Okay, so for this problem, the big difference is that most of the time so far, we've been given the initial amount. But if you read through the numbers in here, we have K, which we've had that before. We have an equilibrium value. Again, we've had that before, but we do not have anything initially. So that's what makes this one different. I'm going to initially write this so that it looks like it has two variables, but then you'll see how I get rid of one of them. I've only got one equation here, so if I were to put two variables into that, I wouldn't be able to solve anything. You have to have two variables with two equations to be able to solve anything. One equation, you can only solve one type of variable. So I'm going to use a big capital I. You could use like a question mark also, but I'm just going to use an I because that is an initial amount, and I don't know it. That's 0, and that's 0. Now we know that I'm losing this one. We know that I'm gaining this one, and that I'm gaining this one. So this is all the same setup, except that I don't actually have a number there. And you'll notice if I were to try to plug that in, I would end up with this. And again, I've got an I, X, two variables, won't be able to solve it. So now what I'm going to do is I'm going to go through and I'm going to put in my equilibrium. So if both the products are this at equilibrium, 0.135 molarity at equilibrium, I also know what this one is. So this value is actually I minus 0.135 molarity. So now I can actually plug this all in. So 0.135, and I can do times 0.135. That's fine. In a minute, I'm probably going to use my squared term to just kind of get rid of that. And then this other term is I minus 0.135, and I have an actual value here, 0.0211. So my big deal is I can't have I in the denominator, so I'm going to multiply both sides by that value. 135 is what I put in there. And actually, while I'm doing this, I'm going to get my ice chart just a little bit out of the way over here. A little smaller too. All right, so now you can actually, I can write that a little bit more neatly. And grab that one too. Okay, so I'm going to set that one right there. And then I can say that my denominator is now canceled out. And I have I minus 0.135. That whole thing times 0.0211 equals 0.35135. And then I'm going, I can't seem to write it, 135 squared. I'm just writing it squared because it's just less numbers to keep up with. You could start putting numbers in and solving it that way. It's just, there are sometimes in science where it's easier to wait till the end to put all the numbers together. Now I need to distribute this to both numbers. So that makes 0.0211 times I, and then minus 0.135 times 0.0211. You could have that 0.211 in the front and back, however you like to see it. Equals 0.135 squared. I needed this term by itself. I do not need anything else in that area. So I'm going to actually add this to both sides. So there we go. Add that to both sides. So plus, plus. And so that part will cancel out. So I have 0.0211 times I equals 0.135 squared plus 0.135 times 0.0211. Now I just need to divide both sides. 0.0211. 0.0211, and then I'm going to bring my calculator over to here, and that gives me 0.135 squared plus 0.135 times 0.0211, and I'm going to solve it and then say divide by 0.0211, and then that gives me I is equal to 0.9987, which if I'm going with all my sig figs, I've got 1, 2, 3 sig figs in all of these. So I've got that I is equal to 0.999 molarity. And if you jump up to the previous section, you'll see that it's actually the same problem that we worked in the green from the other video. And you'll see that the initial amount in that case was actually 1.0 molarity, which is enough in the error to be just fine. So that's how you go about solving for something that has an initial, is that you take your equilibrium amounts, you use the initial as an I, take the equilibrium amounts and plug them all in just so that you only have one variable in the equation. And then you go about solving it as you want to.